Yeah. Oxidation. So we're looking at oxidation of alcohols. Okay. So this reaction also, oxidation is a part of, it's a part of reaction where, oh, this is a completely different set of reactions क्योंकि इसमें CO bond is not breaking in this case, unless it's like alcohols of tertiary alcohols. Sorry, oxidation of tertiary alcohols.
Is this part of cleavage of CO? Oh, this is not.
This is not, क्योंकि इसमें we are not breaking the CO bond. The oxygen is still there. Okay. So in grade 11, you guys had like roughly oxidation of alkanes. If you oxidize hydrocarbons, you're going to get alcohols. And I'm not sure how many of you remember, but you know what is the order of oxidation? Like as you keep increasing the strength of oxidation, or if you allow that extent of oxidation to go on. So hydrocarbons.
Alcohols, then aldehydes, then aldehydes, ketones for
Yes.
primary and secondary, and then last is acids.
Yes. So this is the order. And because we're talking about alcohols, even when you start with alcohols, you get the same thing. Oxidation of alcohols will give you aldehydes or ketones. And this on further oxidation is going to give you carboxylic acids.
This comes under cleavage of OH1. Or
yes.
What's the heading? Yeah.
Just say oxidation. Yeah. Okay, so the generalized thing, what happens during this oxidation is, alcohols are, you have COH and यहाँ पे H भी है. So this bond is going to break, this bond is going to break, and that is how alcohols are turned into aldehydes or ketones. Now, because there are two hydrogen atoms being lost here, it is also called dehydrogenation. Okay. So do you guys remember preparation of alcohols from reduction of aldehydes and ketones? What was happening in those reactions?
Sorry, could you repeat?
You remember preparation of alcohols by reduction of aldehydes and ketones. Like if you start from aldehydes or ketones, how do you get alcohols from that?
You remove
Nickel, LiH4. Yeah.
So hydrogen with nickel or palladium, and then you had LiLH4, and you had NaBH4. So what's happening in that reaction?
reduction reaction by removing the oxygen.
Whoa, where are we removing the oxygen?
Or like if
No,
you
we're adding. No, we're adding a hydrogen.
Hydrogen,
The double
sorry,
bond
yeah.
for ketone.
You're adding hydrogen on carbon and oxygen. That's how you're getting the alcohol, right? So this oxidation is exact reverse of that process. So you're removing those hydrogens in order to get your aldehydes and ketones back. Okay. So this on further oxidation, if you use really strong oxidizing agents, then that's going to get oxidized into carboxylic acids. Like यहाँ पे एक OHP add हो जाएगा. Yeah. But yeah, now we're looking at oxidation of alcohols only. So this is essentially what is going to take place. Some things that you need to remember are, or like, it just makes sense, right? So if you start off with primary alcohols, so primary matlab you have alcohol in the end of the chain. You have RCH2OH. So this on oxidation is going to give you, remove one hydrogen here, you're going to get C double bond OH, which is basically an aldehyde, RCHO. And same thing with ketones. If you, secondary alcohols. If you take secondary alcohols, you've got alcohol in the middle of the chain. So if you remove this hydrogen and this hydrogen, what you end up is R C double bond O R dash. So that's why, depending on which alcohol it is, you will get either aldehydes or ketones. So primary will give you aldehydes and secondary will give you ketones. What do you think will happen in the case of tertiary alcohols?
How would it react? I mean, there's no hydrogen.
Exactly. So you won't get aldehydes or ketones. You need to use, so usually there's like no oxidation. Oxidation will happen, or like instead of saying no oxidation, let's say it won't happen under usual conditions like in the case of primary and secondary. You need to use extremely strong oxidizing agents.
The MnO4.
Correct. Permanganate. Like KMnO4. And very like extreme reaction conditions, like elevated temperature, like higher temperature. Then the carbon-carbon bond itself breaks, and then you'll get like a mixture of carboxylic acids. In case of tertiary alcohols, you need to use really strong oxidizing agents and elevated temperature. The carbon-carbon bond breaks. Carbon-carbon bonds break, like, and you get gives mixture of carboxylic acids. Smaller carboxylic acid. Like if you start off with acetone, you'll get a mixture of, sorry, not acetone. We're talking about tertiary alcohols, right? If you start off with something like this, then you'll get a mixture of formic acid and acetic acid, things like that. Like carbon-carbon bond itself breaks and you get a mixture of the smaller carboxylic acids. There's no place here, just note down mixture of lesser carboxylic acids. Lesser matlab the number of carbon atoms reduces basically. You won't get butanoic acid. You'll get mixture of formic acid, acetic acid.
So if like the structure which you have drawn, this carbon-carbon bond would break and it would form one, like there are two, like so ethanoic acid, and then the second, like the one carbon that will form methanoic acid, like that.
Yeah, like again, there is no predictability of exactly which bond may break. That's why you end up getting mixture of multiple acids. In this case, ethanoic acid and methanoic acid, because there's only 4 carbon atoms. If you take
Yeah.
a bigger one, you may get propanoic acid plus methanoic plus ethanol, that way. Okay, so once you've written this, I'll give you guys a list of oxidizing agents and what their specialty is, like which ones take you all the way to carboxylic acid, which one takes you to aldehydes only, like stuff like that. Under what reaction conditions?
And the oxygen comes from KMnO4, like
Yeah, that's an oxidizing agent. So KMnO4 and potassium dichromate. These are popular, really strong oxidizing agents. So these are like the strongest oxidizing agents. So MnO4 minus, this is permanganate ion. And then you have Cr2O7 2 minus. So K2Cr2O7 is potassium dichromate. So this is dichromate. This is permanganate. So these two are strong oxidizing agents.
Do we have to remember like copper and the MO?
Yeah, I'll give you guys that whole list of what the things are.
Ma'am, I had a couple more doubts in the haloalkanes QT, so can you solve them at the end of the class?
End of the class, yeah.
This and the chiral.
Oh, huh. Like I mentioned, right? I ordered a set. Abhi tak aaya nahi. It'll take some time because it's coming from somewhere outside. So I'll try and use pens if that, but I don't have enough pens and enough hands for that. I have to figure out a way 3D kaise kare.
What is Cr2O7 called?
This is the dichromate ion. Dichromate. Okay. So the compound that is used is K2Cr2O7, which is potassium dichromate. Which is that
What happened to
orange
K?
color. Huh?
What happened to the K?
So,
Like,
so what you use in the laboratory is K2Cr2O7. Salt है ये dichromate, potassium dichromate. Oxidizing के लिए, the dichromate ion is the one that
that we need.
yeah,
Ah.
that causes the oxidation. Same way,
Like you can use Na also, no? Na2Cr2.
Yeah.
That's why only the
most common stuff like what you find in laboratories and by default is K2Cr2O7. So potassium, like permanganate, is like that dark pink purple color, and dichromate ion is a bright orange color. Okay. Sia and Smira, let me know when you guys finished writing. I'll give you the list of oxidizing agents.
I have kind of a silly question, but a lot of the times we want one particular component of a bigger compound, but then in the reaction we use, like in this example, we have suppose we use KCr2O7, but we only need Cr2O7 for the ion for the oxidation. So how do we know that K won't come in the middle of the reaction? Like we only need that particular, so wouldn't we in the reaction use that particular ion? Otherwise, like other things that come with it
Yeah.
metal.
Another advantage with using, like why we prefer using KMnO4 K2Cr2O7 is potassium is very, very electropositive. So it prefers staying as K plus only. So if you have metallic potassium, this wants to get converted into K plus. Agar ionic potassium hai, the chances that it's going to take an electron and get reduced to potassium is very, very, very less. High electropositivity hai. So if you already have K plus, the maximum it's going to do is get attached to a negative ion to form a salt like KCl, KOH, jo bhi hai. But since a lot of these reactions, you're already doing it in a medium where it's dissociated into ions, that also is not going to happen. Even if it joins in, like hydration and all will come, it's going to split. So that's another thing. That's why you don't come across copper salts or lead salts or iron salts because they have their reduction potential is very less. Like they have a tendency to get reduced easily. They oxidize other things easily. So that's another thing with potassium. Yeah. Sodium and potassium. That's why a lot of salts you use where you require the anion, they happen to be like, even in the previous substitution reactions may use aqueous KOH or alcoholic KOH that way, or NaOH for basic hydrolysis. That way the positive ion is not going to interfere in other things. Okay. All right. Here's a list of
What
oxidants.
did you?
Huh?
Sorry, what did you say about copper salt?
So copper is not very reactive, right? It doesn't mind staying as copper metal. Like if you have Cu or Cu2 plus, they can get reduced to Cu quite easily. So it all depends on how much energy it's going to take for this conversion to happen. So the risk with using copper, lead, iron, like the less reactive metals, so like you can't predict if they're going to interfere in the reaction, basically. So if this takes over and what you want is not going to happen, that's difficult. Okay, so oxidizing agents, you have acidified KMnO4. So this is basically you use KMnO4 salt, add a couple of drops of sulfuric acid or HCl, like basically acid medium. So if you remember your redox reactions chapter May, when you had to balance the reactions, you usually were mentioned if it was acidic medium or basic medium, right? This is like an acidic medium wala thing. Yeah, acidified KMnO4. This is a strong oxidizing agent, and this gives you carboxylic acid directly.
I forgot. Like, why did they have to mention if it's acidic or basic?
No, I didn't say why. Like I said, usually.
Like, it's always mentioned when we are supposed to like balance it. It's said it's in an acidic or basic medium. So why is that? I don't know.
See, a lot of mechanisms, if you observe, they're triggered because there's an H plus ion attacking or an OH minus ion attacking, like what do you call it, electrophilic center or a nucleophilic center, right? So yeah, so that where is that H plus or OH minus coming from? From the medium. That's why you make the medium acidic or basic depending on the reaction.
So if there are H plus ions released in that particular reaction, you would keep a basic medium, not to neutralize.
That depends
Or
on
like
the environment. Like if you look at the previous elimination reaction, the first step, you have an H plus coming and attacking the lone pair on oxygen, right? In order for the reaction to proceed, you need H plus ions there. So you're going to make the medium acidified. Same thing is happening in esterification also. Like, to start off the whole thing, to trigger the reaction to take place, if you have like an H plus ion that is required to do something so that the electrophile or nucleophile can come and attack it. So for that reason, like the H plus or OH minus, whatever it is, needs to be there, right? It needs to come from somewhere. So you make the medium acidic or basic, depending on what you need. So again, the neutralization thing that you mentioned, so that's why it's like a lot of reactions are not single step. So once a reaction is kicked off, if you don't want like the reverse reaction to take place, or if H plus is a byproduct and you want to get rid of those ions, then you add the opposite one, like to neutralize it, so that you take away the product. Okay. The next one is anhydrous CrO3. So this is less stronger than dichromate. So this is going to give you aldehydes or ketones depending on primary or secondary. Yeah. Next, we have PCC. Full form is,
Is this strong or weak?
weaker than KMnO4 for sure. This is not going to, like tertiary there's going to be no reaction. So you can just note it down here. Tertiary alcohol, no reaction. Not going to oxidize, not capable of oxidizing tertiary. So PCC full form stands for pyridinium chlorochromate.
So in like CR207 is a strong oxidizing agent, but CrO3 is not as strong as CR207.
Cr2O7 2 minus. Don't forget about this.
Yeah.
So PCC full form is pyridinium chlorochromate. This also same thing, aldehydes and ketones. Does not oxidize tertiary. And with this, you can't go one level higher also. Okay. And so heated copper at 573 K.
So for primary and secondary, it's only one step oxidation, then again further oxidation to become carboxylic acid if it's strong. And
Yes.
if it's weak, then it's only till aldehydes or ketones.
Yes.
But for tertiary, it's directly carboxylic acid. It
It's all
won't be
or
aldehyde.
it's all or nothing. That's why I was about to say tertiary ke saath no oxidation. But if you have like something like acidified KMnO4, then the compound itself breaks apart and everything gets converted to carboxylic acid.
Okay.
Nothing else works on tertiary. Heated copper. So heated copper tube ke saath, this is special. So you have the same thing, aldehydes, ketones ke saath you have primary, secondary. So aldehydes from primary, ketones from secondary alcohols. In this case, with tertiary alcohols, this is going to result in elimination, like dehydration reaction.
Ma'am, all these CU, PCC that we're using, no, not that, sorry. Yeah, KMNO4, that we're using on alcohols or aldehydes and ketones, like to give acids, that are using that on alcohols or aldehydes and ketones.
Anything. If you use KMNO4, you're going to get acid, whether you start from alcohol or aldehyde ketone, jo bhi hai. This is, in fact, it's hard to control. You can maximum maybe reduce the temperature. You can dilute it, like cold dilute KMNO4. Still, like risky, which is why you have these other oxidizing agents, specifically if you want aldehydes, ketones. So yeah, so heated copper, how this is used is basically you have copper tubes, you heat it up, and then you pass the whatever alcohol, like the gaseous state, through the heated copper tube, and then the reaction takes place. Once that's done, what you get are the oxidized thing. In tertiary alcohols alone, instead of oxidation, they undergo dehydration with heated copper. That's an exception. That's a different thing. And again, you can see why tertiary alcohols, because see, in all these cases, oxidation is taking place because of the removal of hydrogen. In the case of tertiary alcohols, then because it's a tertiary carbon, it's a different mechanism that it takes place. OH is removed, you have a tertiary carbocation being formed, and then H, then one of the hydrogens from an adjacent carbon is removed, and you end up with dehydration.
So dehydration, the H is from the carbon that is adjacent to the carbon where OH is attached, right? Because that one doesn't have any.
Yeah. So H or OH nikal diya. So what is the product if dehydration takes place?
Wait, I didn't understand H, which is adjacent to what?
So I'll give an example. I'll give a reaction.
How can there be another H? Isn't it tertiary? So it will just be C, Z, C, and then OH, right?
Yeah. But it won't be just carbon, no?
Oh, like that.
These also will be filled, right? So this, if you pass through copper at 573 Kelvin, dehydration है ना? So minus H2O होना चाहिए. So OH and a hydrogen gets removed. So what do you think the product will be dehydration के बाद?
An alkene.
Alkene is absolutely correct. Yeah. CH3. OH हट गया and यहाँ पे CH2 है. So there'll be a double bond here. So heated copper at 573 Kelvin, like heated matlab take it to this temperature. If you pass primary alcohols, you'll get aldehyde. Secondary say ketone. Tertiary say you get alkenes. Okay.
This chapter is so hard.
It's not hard. It's just lengthy because you have lots of applications, lots of reactions that alcohols undergo.
And this time we only have haloalkanes, haloarenes. In like final, we'll have the the other chapter, this and haloalkanes. The one with carboxyl.
But the thing with organic related questions is that there's a lot to learn, but questions will all be like, you'll start off with a haloalkane, and then that on reaction with alcoholic KOH gives you a product B, and that on, when you react with dilute sulfuric acid gives you a product C, and it'll be that kind of question. So it's like a mixture of haloalkanes, alcohols, aldehydes, like pura mila ke.
So, ma'am, that's not easy. In like the answer key, they've done 10,000 different reactions from God knows where, and they've put it and they expect us to liquid NH3, NeNO2, anything they just done and they're getting the desirable. I'm so confused.
We'll do the questions baad mein. And another thing is a lot of reactions will also be repetitive. See, preparation methods from alcohols to haloalkanes jo seekha hai, here it's repeated as chemical properties of alcohols. So यहाँ पे you're studying reduction of carboxylic acids and oxidation of alcohols, right? The same thing will be repeated in aldehydes, ketones, where it's preparation of aldehydes, ketones. One method is oxidation of alcohols. So there's a lot of overlap also, which is why I'd suggest whenever you're sitting with organic chemistry, rather than having separate chapter wise thing, like, okay, do it first time, but keep like a separate chart or notes or something where you're listing out all the reactions. Like it should be like, okay, if I take this raw material and treat it with this reagent, then I'm getting this product. Then that reaction is that reaction. So it doesn't matter whether you're studying under preparation or chemical properties or what it is. If you're given a reagent and that raw material, then you know that, okay, hamesha ye reaction matlab yahi produce hoga. So studied in that way, it'll get easier. Like at least application based questions you'll be able to answer easily.
But like there's so many, so it's in my head now fixed ye reactions are from haloalkanes and these are from alcohols or whatever. So it's hard to call back to the reaction.
Yeah, if you're able to do it chapter wise, that's easy. But otherwise, yeah, like this is another.
No, that's not a good thing, because like from what I understand is whenever we see a question, we be like, "Arey, ye alcohol se hai." So then we start thinking. It's not a good approach, actually speaking, because first I'll see the question and I will only understand it after I understand which chapter it is from. Like ideally, you should be able to see the reactant and know what the reaction is, which is not happening.
That's okay. If compartmentalizing helps you figure it out. Like end of the day, you just need to know if you have this raw material reactant with this reagent, kya produce hoga. So that's all that.
But the thing with compartmentalizing it, you remember it in a specific way. So even if there's like a little difference, suppose the reagents are different, or we don't remember the name of the anything that's a little bit different, or some from or it's like a combination of something from alcohols and haloalkanes. It's hard to it gets all mixed up, so it's a little hard to remember and recall.
Okay. Cool.
Is just beta elimination.
This one, yeah.
Yeah.
Beta carbon से हो रहा है, yes.
But beta elimination is with alcoholic KOH, right?
That's just like a mechanism. Like, okay, if you use alcoholic KOH, that is happening. Here also essentially same thing, right? You have OH and then beta carbon say one hydrogen is getting eliminated.
See, ma'am, this is the same thing happened. In my mind, beta elimination from that chapter is alcoholic KOH. If I see it somewhere else, I'm like, what is this?
So associate it with the correct thing. Like don't associate with the reagent. See, when it comes to mechanisms, okay, kya ho raha hai? Like if it is being triggered by, see, like the thing is alcoholic KOH, you need a strong base. That is what C2H5O minus is doing. So maybe you can achieve that with a different base also. So associate it with the mechanism, and then yeah, like even if you remember it, yeah, associate the right things with the right this thing. Okay, that's it.
But the only way we can really differentiate is by the reactant. Like isme alcoholic KOH, so beta elimination. Then wherever there is nickel or like platinum, we know ki it's
Hydrogenation.
hydrogenation. Yeah,
That's an easier way to remember.
And I
to remember.
okay. Okay, so primary, secondary, tertiary, sab kuch ho gaya. So there's a biological thing, like okay, this is all like laboratory based. PCC, you use it in industries because this usually gives a good yield of aldehydes or ketones. For the ease, like logistics wise, you can use heated copper tubes also, which is why we've listed like these three specifically. Biologically also, enzymes also helps with oxidation. So that's what happens. So when you consume alcohol excessively, what happens? Like what is the, like what part of your body is affected?
Liver.
And that is because there's enzymes in the liver that is produced that converts alcohol into aldehyde. That's essentially what's happening. The liver is processing all the alcohol, converting into aldehyde, which is again gotten rid of. So that is the reason why if you have denatured alcohol, matlab thoda sa methanol, if it is mixed, if you consume that, that is the reason it acts as a poison and your basically blindness happens, death happens. Okay.
Why? What's the difference?
The reason is that so both ethanol, so if you have ethanol and methanol, this is denatured alcohol, right? It's a mixture of both of these. So on oxidation, ethanol gives you acetaldehyde, ethanol, CH3CHO, and methanol gives you formaldehyde, HCHO. So formaldehyde is the one that's dangerous, that causes harm. So if somebody by mistake, like if they're poisoned with methanol, if somebody was poisoned with methanol, this is the reason the treatment is give them more ethanol, because in the liver for that enzyme, ethanol is more preferred to methanol. So if there's enough ethanol coming in, that like you won't get any formaldehyde out of it, because that enzyme preferably attacks ethanol to methanol. And while that's happening, you can, make that person pukes up the stomach to get rid of all the poison, basically. Okay, that's a thing. So basically, okay, I've written it like what written here is swamp the enzyme which is responsible for oxidation with ethanol until the HCHO is flushed out of the body.
Ma'am,
Hmm?
you go back.
Yeah.
So the dehydration is not oxidation, right? Like that's not. That
Yeah, so that's why I've written it in a different color. With tertiary alcohols, there is no oxidation that takes place. So if you treat it in dono ke saath, there is no reaction. With this, you get dehydration instead of oxidation. That's it.
so basically you
your,
can't go beyond. Sorry. So
One of
basically you can't go beyond that, right?
no,
With
that's it. Yeah.
tertiary, it's either no reaction or it's not giving us oxidation, unless we use the extreme conditions to
Yeah.
give acid.
what is the good yield written?
So good yield, matlab you get lots of aldehydes and ketones, like percentage wise, before the reverse reaction kicks in, and in terms of the rate of reaction also. If you let all these things run for an hour, this will give you maximum quantity of
So
aldehyde.
is it like industrially used or something?
Yeah. Okay. Guys, a little correction. I remembered this wrong. So acetaldehyde, formaldehyde, this further is processed into acids. Like basically in the body, oxidation takes place. This is converted to CH3COOH. This is converted to HCOOH. CH3COOH is basically vinegar. Your body can deal with it, no problems. But HCOOH is something your body cannot deal with. Yeah, this is formic acid. This is the stuff you find in like insect stings and all that. So that's why your
The
body,
ant bite wala,
ant bites, wasp bites.
So basically, our liver has strong oxidizing agents. That's why it becomes acid.
enzymes in the liver convert.
Yeah, yeah,
That's strong oxidizing.
yeah. I won't say it's equivalent to permanganate, but again, they have their own things, right? Maybe they are capable of oxidizing this, but not anything else. Permanganate works for like, it's like a universal oxidizing agent.
That's so convenient that they just oxidize what people want to have.
Yeah, it's not on purpose. I'm sure there were other iterations, but people just died out, evolution. Smer, are you there?
Yes, ma'am. I'm just put off my video.
What happened?
I'll just put it on in like 5 minutes. The connection was weak.
Okay.
Ma'am, you
Hmm?
had mentioned when we were doing this before, you had mentioned that after ketone, the chain breaks. Like that was what you said. That was what you said. So what does that mean?
Oh, see. Just write down this thing. So let's say you have CH2OH gives C double bond OH. Then oxidizing this is pretty easy because like in place of H, oxygen gets inserted, which is why aldehydes can get converted to carboxylic acids. End of the chain, pretty straightforward. When it comes to ketones, so we have CH2, C double bond O. We start off with alcohols, right?
These both are with strong oxidizing agents, right? These both take place in the presence of strong oxidizing agents, right?
You'll need like stronger than CrO3 and stronger than PCC. Yeah. They're the right oxidizing agents. So this will like hydrogen nickel gaya, so you get ketones. So basically it's CH2, C double bond O, CH2. Abhi, if you want to oxidize this further, like inka valency is completely filled, right? So it's not as easy as
bond that's free to accommodate the
yeah, it's not as easy as with aldehyde. So either this or this needs to break in order to oxidize it further. So ketones are more difficult to oxidize, but we'll look at how to oxidize ketones, what agents will oxidize ketones when we study about ketones. Okay. Yeah.
So what's
that's-
about breaking the chain here?
Yeah, that's what. Like if in case we want to oxidize this further, we're breaking the chain here. This has to break or this has to break if it needs to get converted to an acid.
Also, what about K2Cr2O7? That is also same like KMNO4.
Yeah.
But what's happening is what's happening with the aldehydes, that also has to break only. So what is the difference?
This is easy because you're not breaking a carbon-carbon chain. Only the hydrogen has to get away. Hydrogen is like tiny.
Ah.
Can break this easily.
So K2Cr2O7 would also give carboxylic acids from primary secondary.
What was the question you asked iske pehle about K2Cr2O7?
I asked if it was same like KMNO4.
Cool. So that's it for reactions of alcohols, guys. So just to summarize, because in a while, we looked at acidic nature of alcohols. So where RO OH. So where this bond breaks, like H plus is given out, so we have acidic nature. Then we compared it with acidic nature of phenols also. Then we had esterification, where again OH bond is breaking. These are the two major reactions. And then we have substitution, like where CO bond is breaking, substituted with halogens. So you have had a set of reactions there. Dehydration, so the whole OH is like gotten rid of, you get alkenes, and you have oxidation reactions. Okay, that's it. Cool. 3 major sets of reactions, out of which one property is not even a reaction. It's like acidic nature. Yeah. Okay. So now we come to reactions of phenols. First reaction, we've been studying this right from grade 11, should be quite familiar with it. Electrophilic substitution. So what is electrophilic substitution? And what is getting substituted here? Am I substituting the OH?
The O.
This is phenol. So if phenol is undergoing electrophilic substitution, what would be the end result? We have studied this like thrice, guys. होता क्या है electrophilic substitution में?
Electrophile is substitute.
Where is it substituted? That is the big question there.
In place of an H.
There you go. That's a start. So
Orthopara.
There you go. OH is ortho-para directing. So that's what happens in electrophilic substitution. What happened, rest of you? Completely forgot. So electrophilic substitution, major thing you need to know is the OH of phenol is activating the ring. Let's write it this way. OH attached activates the ring. Activating the ring matlab it's pushing electrons into the ring at ortho and para positions. Okay, so quickly I'll give you guys different reactions. Tell me what products you get. First being nitration. Do you remember the reagents for nitration?
Nitric acid and sulfuric acid
Yes.
concentrated.
OH. Yes. Okay, phenol, presence of HNO3 and H2SO4 gives, what would be the product here?
OH and then an NO2.
NO2 in ortho and para.
Yes, OH, NO2, and you have OH, NO2. This is the basic reactions, what happens usually.
That boiling point, melting point one, boiling point is polarity, no? And melting point is symmetrical.
Isn't it opposite?
And what?
They're pretty related, like both of them relate to, so melting point, the extra thing is how, like when the solid is melting into liquid or liquid is stacking up into solid, how the molecules are arranged. So in that case, the symmetry, like the branches and all, how they stack up, all of that matters. But for both boiling point and melting point, the polarity and intermolecular forces, all of that matters. Because for when you're boiling or melting, they literally have to overcome the intermolecular forces. So that relates to your polarity, hydrogen bonding, all those other things.
What, Arya?
It's not opposite. Melting point the reason is how symmetrical it is. So it is well fitted in the crystal lattice. So that's why para is most, and boiling point ke liye polarity.
It's not even like it's a specific case of polarity. So how do you separate both of them, ortho and para?
Distillation, na?
हाँ, तो which one will you distill? Like किसका boiling point ज़्यादा होगा? किसका कम होगा?
Ortho.
हाँ,
Ortho only, na?
ortho will be separated out first, yeah. Uska boiling point will be less. So you'll get this first and then you'll get this.
No, miss, ortho is highest now because it will have more polarity. So more boiling point.
No. See, ortho ke case mein, let me structure. So this is what ortho looks like. So you have oxygen, hydrogen here. You have nitrogen, and of course, like baju mein oxygen. And you have para.
If it's more polar, it should have less boiling point, na?
No,
Easier
like don't
to break.
generalize it that way. Like in terms of polarity, both of them have the same, like hydrogen attached to oxygen and then nitrogen attached to oxygen. Yeah. But what is the major difference between both of these?
H bonding can take place in
Position of
ortho.
nitro.
Yes. Do you guys remember there were different types of H bonding?
Yeah, so in ortho
Yeah.
it can be intermolecular.
Huh?
Sorry,
Inter and
intramolecular.
intra.
Yeah.
And यहाँ पे इंट्रा का कोई सीन नहीं है, both of them are on completely opposite ends.
So
Yeah.
Will bond to other molecules. So abhi, based on this, which one will be easier to, like, which one can evaporate off quickly?
Para.
Huh?
Para will be easier.
Para.
No.
Yeah, the one which has inter will be easy.
How will this evaporate off if this is attached to other molecules in the liquid?
But isn't
Because it will be
intra
easier
like
to
stronger?
break.
How will
Yeah.
it be easier?
Yeah, because it will be easier to break the ones that will be attached to other molecules rather than between, like in itself.
But you don't want to break the bonds within it. Like, think of what are the intermolecular forces
it will be
in this case and in this case.
because it's inside, no, it's within itself, so it
Oh
won't
yeah, we
have.
asked Miss the same things in school also.
No, I didn't understand. I didn't get it.
I was the one who asked this exact same question and again I asked. Genius.
You
It's,
explain
so
it.
Miss,
Hmm.
so basically Miss said that it is always easier to, like we don't want to really break the bonds within the molecules. So abhi usme H bonding hai, it will be easier for you to break the bonds which it forms with other molecules. So matlab, right now I'm saying, or I'm saying ulta.
No, you're saying ulta.
Ulta, sorry. Wait, so the ortho one would evaporate faster because it's not forming any bonds with other molecules. So, मतलब वो खुद में ही H bonding कराएगा. So it will be easier for it to evaporate rather than para, which is forming bonds with other molecules. So first you'll have to break them for it to evaporate. But in case of ortho,
Wouldn't
it's
it be
forming within
easier to
itself.
break an intramolecular bond
But you
versus
don't want to break, na. So if you have to evaporate, you'll break the, and if you have ortho and para, in the ortho it's not forming H bonding between the other molecules. So they will be able to evaporate easily. Whereas in case of para, it is forming दूसरे molecules के साथ. So for it to boil and then like evaporate, it will have to break the bonds between the two different molecules. You don't want to break the bonds within the same molecule.
See, what is evaporation? You're separating out the molecules. Like liquid state may they're very close to each other. Gaseous state may they go far away from each other. In which case, can you separate molecules more easily? That's what you need to look at here. Ortho mein, because hydrogen bonding is within, you don't care whether this is broken or intact. All you care about is, can I separate these molecules easily? And because there is no extra forces between the molecules, you can separate them out easily. So, matlab ye,
So we don't care to break the intramolecular bond because that won't help in the evaporation. We want to break the intermolecular.
yes. It's maybe,
Is there a major minor product for nitration?
huh? No, orthopara is pretty much 50-50 because you have electron density on both the ends. Meta will
But
be
what about
very minor.
para being more because of its symmetry? Because it's more stable, something like that was there.
Like that. It's maybe stability RS, maybe stability RS, nothing like that. See,
It was there in haloalkanes, na?
Yeah, it was
Para.
there. Para is more major product because it's more symmetrical. So
But I don't remember seeing major minor. It is true that para is more symmetrical, but
that's it.
So it was major because
no, but like if it's more symmetrical, why would it form more? What's
Yeah, like forming.
it's more stable. It wasn't haloalkane.
But
what?
whenever we want to decide which is major, which is minor, like even in case of carbocations, we always see the stability. So if it's more symmetrical, it'll be more
Stability
stable.
of what? Not the end product, of the intermediate.
Huh?
So we're saying that in the end product, whenever we have to decide, we always say that para is the major product because it's more symmetrical. So it'll be more stable. Less.
But it's not like a very intense difference. That
Like
I
for
have to
example,
run
in halogenation, when there is when we use any like the minor product is the ortho one and the major product because of the symmetry is like the para one. So
Can
the
you
one with Cl which we use chlorobenzene reactions.
chlorobenzene with
halogenation, like any Lewis acid or electrophilic substitution. Under electrophilic substitution reaction with chlorobenzene, when you do halogenation, there are two products that is formed. One with the X at ortho position and one the X at para position. In that case, we write minor and major because para is symmetrical, so it's the major product.
Okay, let me look into that. The difference is not as
Where is
large
this?
as it would be with.
I'm sending a picture.
Like haloalkanes, man.
Yeah.
Alkenes होगा? Yeah. Yeah, so it's not a very stark difference. There is a slight preference for para. It would be more like 47 versus 53 or something like that. It is not as stark as, oh, am I going to get ortho para only or can I get a meta product also? So ortho para will be like 95%, meta will be like 5%, 3%. But the difference between ortho and para itself is like, it, even if it's not like completely 50-50, it's more like 48-52 or 47-53. The slight preference for para. It's not like a very it's not a major minor. There's a preference for para product.
But it's weird how उसके नीचे nitration है, उसने तो नहीं लिखा है major minor in the
Yeah.
picture that I.
Yeah, like if you're specifically nitpicking comparing ortho para mein, then you kind of say there's a preference for para, but you won't classify it as a major minor product because it's more or less equal. Like there'll be maximum like 5 to 10% difference between the yields. So rather than saying major minor, that would apply to ortho para versus meta.
Also for
It's a slight preference.
halogens, for halogenation, both were halogens. In this, one is OH, one is nitro. One is withdrawing and one is donating. So it
But
would be
also end
different.
products hai na? Like when you're predicting the products, you only need to look at the reactants. As you said, it can get pretty crowded at the ortho position. So because of the symmetry and everything, there will be a slight preference. But if you look at it, it is equally activating on ortho and para positions both. So there won't be like a very intense difference. Not enough to think of it as a major product, minor product. ये थोड़ा सा ज्यादा होगा, but that's it. So in this case, minor product will definitely be meta. That's like single digits. It's like if you compare ortho plus para and then meta, it's more like 95% 5% or 98% 2%. That way, it's like very, very tiny, negligible amount. Between ortho para itself, it's, yeah, it might not be 100% equal quantities with a slight preference towards para, but it's not like ortho will be negligible amounts. It's not like a minor product. You'll get a good chunk of ortho also. Some cases, yes, like aniline and all, when one of the products gets When there is a meta directing possibility, then you may get like meta product also, but not in this case, not right now.
Ma'am,
Hmm?
why does nucleophilic substitution not happen in meta? Like I know it happens, like suppose haloarenes, it happens under very only extreme conditions. But why is the nucleophile not attracted to the meta position? Because that's electron deficient, right?
No,
Compared to orthopara, which are electron rich meta, mein to there's not that much electron density, right?
compared to it, like that nuance matters. Nucleophiles are, they themselves are electron rich, they are attracted to positive charges, they are attracted to the nucleus itself. But if you look at any benzene aromatic uh, compound as a whole, you have all these pi electrons around the ring that's very, very electron rich. So if you get another electron rich compound close to it, it's going to this thing. So even in this case, as I said, like there'll be 0, 1, 2% at meta position also, but it's small enough that we call it major product, minor product, and we can neglect it. And also, we are talking about electrophilic substitution, right? So anything that likes electrons, that itself is electron deficient and it's attracted to electron rich areas, are going to come towards this ring. They have multiple options, but the reason why we say ortho-para directing, meta directing is, if you look at the resonance structures, there is an outright negative charge concentrated at ortho and para positions.
Yeah.
Whereas यहाँ पे कोई charge नहीं है. मतलब this has extra electrons compared to the meta position thing. इसलिए you have like ortho. That's what creates the ortho para directing and all that.
That I understood. I was asking about the nucleophilic substitution.
Huh.
So I thought that would be electron deficient.
Just because this is electron rich doesn't mean this is electron deficient. So that's a detail. Okay, so this is nitration. A few more things. Considering this is phenol, considering the reactivities and all, this reaction is capable of taking place even with dilute nitric acid. In fact, you should use dilute nitric acid if you want to substitute just one nitro group here. So if once, yeah, let me continue. So
Yes,
if
could you let it?
Huh?
1 second, last.
not done with it, okay.
Ma'am, but I thought that nitration was for concentrated.
This will
We
like
had done
basically you
that
need
last year.
yeah, you need NO2 group, and last year you done it with benzene. See, our reagent is not changing. We're using nitric acid only. And depending on the reactant, like obviously some are more reactive, some are less reactive. You can manipulate that a little. This reaction will take place if you take concentrated nitric acid also. So we'll see what happens if you do that.
Even in the chlorobenzene one, we use concentrate.
इसमें भी use कर सकते हैं, just that the product will be a little different.
Do we not use concentrated H2SO4 because it's like a dehydrating agent, and so
Nothing like that. We use concentrated H2SO4. That causes sulfonation. Right now, we're still looking at.
We have to remember like 3 different.
See, yeah, now there's something up with. Okay, we'll see what happens if we use concentrated nitric acid. She's stuck. I think she'll rejoin. So if we take the same phenol and use concentrated nitric acid, then the same reaction will take place, just that it's going to take place like a lot. So all the available position are going to get substituted with the nitro group, and this will be the end result. So it's not terribly different. It's just the rate of reaction it's milder here. So you just have a single nitro group substituted. Here, because you took concentrated nitric acid, it just like, yeah, it just up
What
itself.
about H2SO4?
H2SO4, what is the, like, if you don't take nitric acid, if you take only sulfuric acid, what is that used for? Like, what reagent you end up getting?
That is for sulfonation, no, not for nitration.
No, like in addition to HNO3, because we needed that in the previous reaction.
That's again, that's a reagent in order to create the nitro group. So obviously that'll be there. But here we are focusing more on dilute nitric acid versus concentrated nitric acid, because nitric acid is the source for NO2. You take a lot of nitric acid, you have a lot of NO2.
And is that concentrated or dilute, H2SO4?
That's like a standard amount. That's you take enough so that you get your required reagent. I just saw what you sent, Arya. Correct it. It's like there is a preference for para, but it's not to the extent of major minor. Like yahan pe we call major minor when it's like 95-96% of one thing and just 2-3% of the other thing. That's not the case. That's not the difference between ortho para. It's more comparable than that. Yeah.
But in the textbook, it's mentioned major, minor.
Acha. ठीक है. But again, make a note of it. Keep in mind that contrast is there. Like meta is the lowest of the lowest, almost negligible. Then comes ortho. It's not negligible. Like even though it's lesser produced, it's not negligible.
Textbook may it's not mentioned major minor for this
Yeah,
reaction.
that's what I'm saying. It's not major minor. No, like we never wrote major minor. It's only ortho.
Oh, I just found another source for organic chemistry. Yeah, this has percentages. This is not phenol. This is an ether group ka example, but gives you an idea of what the percentages are like. So this is like OCH3 alkoxy groups are orthopara directing, but you can see the contrast between how much quantity. Obviously, it's not going to stay the same for every single substituent you have here, but gives you an idea. So 30 to 40%, 60 to 70% compared to meta, which is like barely there, less than 2% in fact. So if this is the kind of contrast we have there, we can label it as, oh yeah, major product, minor product. But otherwise this is significant enough that we can't neglect it. So that is why we say ortho, para, or major. That is why in this case we can't put the label of major and minor. So you can write it as there's a preference for para direction, but that's not dominating over ortho.
So in this also,
Mhm.
I sent a picture. Sorry, we're probably stretching this too long, but
Just Here they mentioned major minor. Okay. Okay, but this is for chlorobenzene. We'll have to check percentages kitna hai. So if it is mentioned textbook mein, theek hai. Put it as major minor. Okay. Now coming back to nitration, you take less of NO2 dilute hai, so mono substitution takes place. But if you take concentrated, because then you have a lot of nitric acid available, all the nitro groups get substituted here. This is like an industrially required product. So this iska naam hai picric acid. So in case you get like an MCQ or something, structure of picric acid is trinitrophenol. All three available things is substituted with nitro. And also this reaction is kind of slow. You can see because there's multiple substitution that takes place. So the yield of this is poor. So if you want to produce picric acid, if you want to increase the yield, then instead of going in a direct method, what you do is you do sulfonation first and then you do this. So this is like the rough reaction. You take phenol, then treat it with concentrated sulfuric acid. So this will give phenol 2,4. So this is called phenol 2,4 disulfonic acid. And this on treatment with concentrated nitric acid gives picric acid. So this reaction, you do it to increase yield.
So this is sulfonation plus nitration.
Yes.
But then why is there no H2SO4 in the second one for nitration?
Again, so medium, like you have like an acidic medium, right? So this you do it in 2 steps where you introduce sulfuric acid first, and then when you kind of have an indication that like this reaction has taken place up to like 80-90%, then you use then you add in the nitric acid. So the sulfuric acid is already there, and when you add the nitric acid, the nitration will take place.
How would we get SO3H in the first place without using SO3 in the reagent?
H2SO4 hai na? Like you're using concentrated H2SO4.
For sulfonation, we always use oleum thing, na?
Oleum is really concentrated sulfuric acid. SO3 plus H2SO4. See, you get H2SO4 in the first place by dissolving SO3 plus H2O. So, iska mixture is sulfuric acid. When you dissolve sulfur trioxide in water, you get sulfuric acid. That is why oleum is produced, because you have like excess of SO3. Then depending on which factory you're sending it off to, you dilute it with that much amount of water to send utna concentration ka sulfuric acid. There's different industries.
I have no clue what oleum is.
So oleum is like extremely concentrated sulfuric acid. It's like H2SO4 itself is sulfuric acid with extra SO3 in it. So oleum, you need to dilute this with water in order to have like usable this thing. This is also called fuming sulfuric acid, by the way, because SO3.
So for so H2SO4 is formed by SO3 plus H2O, and then fuming oleum we get by adding extra SO3 to it.
Yeah, it's really concentrated with sulfur trioxide. Then you add enough water to have whatever concentration you require of sulfuric acid. क्योंकि एक बार dilute करने के बाद उसको concentrate करना is difficult. It's easier to dilute to the required level rather than do it the other way around.
So in this one, first you're adding concentrated H2SO4, right? And also another difference is in the previous one, it's not concentrated H2SO4.
No.
In this, it's concentrated.
Dilute, yeah.
But in the nitration that we had studied, that was concentrated H2SO4.
Because we started off with benzene in the first place. यहाँ पे because you're taking phenol, you already have a little bit of acidic this thing.
Just randomly write dilute and concentrated wherever you feel like you'll get it right. It doesn't.
No, it's not random. See, you can't use concentrated to get a monosubstituted product because phenol is more reactive than benzene, clearly. That's a pure hydrocarbon. There's like oxygen there, there's polarity there, all of that's happening. That also matters, no?
Ma'am, how are we getting from SO3H direct? How are we getting NO2 in picric acid? Like,
We're not looking at the mechanism. It's not like a direct thing, but yeah, production of picric acid, matlab, you first convert it to.
There are intermediates to it, right? So there are intermediates to it, right? It's not like substitute for anything.
So picric acid is it's a compound. It's bright yellow in color and it's used as an explosive like in the military, which is why you can see the significance. It's a harmful compound. It's not something, because it is bright yellow color, it can be used as a dye, but it's also used as a raw material for like explosives and stuff like that. Basically, it's a commercially important product. It's got a lot of uses, which is why we are like having to study extra about it. Okay. Next we have halogenation.
Ma'am, 1 second.
Yeah.
The 3 NO2s, is it like a combination of orthopara or is it actually like 3 NO2?
No, it's 3 NO2. If it's a combination, we write it separately, like we did.
Yeah.
Here. Like no, it's a polysubstituted product. 3 of them get substituted.
Done.
Okay. Next we have halogenation, same electrophilic substitution में. What do you guys remember about halogenation reaction? Like when we were doing it with benzene, when we were doing it with chlorobenzene, like what was the reagents you guys used? What was the product?
Anhydrous ClCl.
Yes. And do you remember the reason why we had to use anhydrous AlCl3?
Because it forms free Cl minus ion or something like it forms AlCl4 minus and then
Yes.
yeah.
Lewis acid.
Lewis acid, correct. Yeah. So Lewis acid, because lone pair on halogens, this attacks the lone pair of halogens, and we want its electrophilic substitution. Na electrophile create karna padega. So the Lewis acid takes away one of the halogens from the compound and creates that electrophile. This is the reagent that ends up attacking benzene. Okay. Now, in the case of phenol, the modification here is that same thing. If you look at bromination, because again, wahan se you get like an industrially distinct product. यहाँ पे इतना strong Lewis acid की जरूरत नहीं है. Like even if you take a low polarity solvent, okay, a low polarity solvent, for example, something like CHCl3 or carbon disulfide. This is fine because we're doing it with phenol. So phenol is because like even in nitration we saw. So this activates the ring sufficient that bromine is easily polarized. You don't need a Lewis acid in order to polarize bromine in this case. So again, it's auto para directing. So the reason why this is so polarization of Br Br2 takes place even without a Lewis acid because phenol is activated. Like so phenol activates the ring enough that you don't need a separate ion to polarize the halogen in order to polarize the bromine to create the electrophile. So that small amount of polarity is sufficient because phenol is doing major amount of work of dividing Br2 into Br plus and a Br minus and then taking the reaction forward. Like phenol on its own is enough to polarize bromine to create the Br plus ion in order to create the electrophile that then gets substituted here. So phenol is activating enough, which is what we saw even in the case of nitration. So dilute HNO3 was sufficient for monosubstitution, but not in the case of benzene. Activating.
So in this, we don't need Lewis acid because polarization of Br2 can take place.
Yes. The whole
I
purpose
don't
of
understand what that meant exactly.
see the whole purpose of the Lewis acid. So polarization, matlab kya hai? Like we are creating poles, right? Like positive and negative. Like that's what happened here. We had a Cl minus that the Lewis acid took in order to create the Cl plus. Jo non-polar tha, that became polar. Like we have a Cl minus Cl plus, Br minus Br plus. Now phenol is activating enough that just a low polarity solvent is sufficient to polarize Br2 into a Br plus and a Br minus ion. So then the Br plus then goes and gets substituted to the phenol ring. So that's what means by polarization. Like the whole purpose of the other reagent was to create the electrophile. What this is saying is, in case of phenol, like if you're having a reaction with phenol, you don't need that external agent. Like a low polarity solvent is sufficient for it.
What happens to Br minus?
HBr, like substitution hai na, H plus gets out.
Oh yeah.
Last step. Yeah.
See, this is what we are saying. Like in this one, you don't need AlCl4, but in haloalkanes, haloarenes, you need this. So it's like different for everything, and it's super confusing.
So that is why remember the skeleton, which is electrophilic substitution, matlab what is being substituted, this thing. So the reason for those things, which is why we don't even mention it as a reactant, we put it on the arrow, is that creates the reactants. Like the actual reaction will take place with Cl plus, but because we can't just get Cl plus naturally, we need reagents for that purpose. So if you're achieving this without this being necessary, that's what is happening over here. But what you remembered for electrophilic substitutions, yeah, like that was sufficient. That was what was required. Electrophile chahiye, substitute kahan ho raha hai? In place of hydrogen on the ring. And you need to remember ortho para directing, meta directing. So these are all like finer points related to are we taking benzene that's completely non-polar, इसलिए lose acid चाहिए था. But यहाँ पे थोड़ा सा polarity create हुआ, so that gets modified a little bit.
ब्रोमीन के लिए कौन सा Lewis acid था? For bromine, what was the Lewis acid that we used?
FeBr2 or something.
FeBr2, AlCl3 also works. That's why don't get hung up on like compartmentalize ki iska role kya hai. What is the role of acid medium? What is the role of this? So that way you can find substitutes. So even if you're given something else in its place, you won't get confused. So again, just like with nitration, like another this thing. So instead of using just bromine in these solvents, if you react phenol with bromine water. So if you treat phenol with bromine water, same reaction, but just like nitration, you have substitution on all the available places. So
Ma'am, sorry for going back to the previous topic, but I remember I texted my teacher a while back if there is orthopara, so I checked that. So she had, so she said that ortho. So she said that in phenols, ortho is major because of intermolecular H bonding. But that was the reasoning we discussed the boiling point, right?
Yeah, that is not making sense. Intermolecular hai, so why is the production of ortho major? Anyway, like I found that website like that gave for anisole for the ether alkoxy group na. So I'll see what are the percentages for phenol, and then I'll let you know.
We'll just write ortho and para for now. Let's not just mention major minor.
Yeah, just put ortho para. You need to.
Sometimes they give you like the description of a reaction and ask you major product.
So उसमें लिखना ना because the question is specific.
Yeah,
No, then
And it's only
what
asking for the
what-
reaction.
you can write ortho and para. Like if a question is asking in that sense, they're comparing between ortho para versus meta. Like what is it, ortho para directing or is it meta directing? That is the large scale difference. Difference
So
between
we won't get.
But when they
between
ask for
ortho-
major minor in questions, it's never about ortho para. It's always about relating to the mechanism. And
Yeah, Markovnikov and yeah.
yeah. So it's always Markovnikov or Setsev rules, or if it is in aromatic compounds, they're looking at, are you going to answer ortho para or are you going to answer meta? That is the major distinction between major minor products. Okay, so about this, so this is like a white precipitate. So you can use this as an identifier for phenol. When you treat it with bromine water, you get a white precipitate.
This is the distinguishing test. One or
This is like a characteristic of phenol, like we're talking about this thing, right? So if you know that you have alkane, alkenes, alkynes, and probably phenol randomly in the mix, this is how you can identify it. With bromine water, you get a white precipitate.
yeah.
So distinguishing test, yes. Otherwise, if you're given in a question randomly, okay, a compound X when treated with bromine water gives a white precipitate, then you can identify, okay, X matlab phenol hoga, and then look at the rest of the question.
From this chapter, the most number of questions would be from like, or that doesn't make sense. Because like when Miss was discussing approximately with what is important, she said that ethers is सबसे important from this chapter.
Ethers is important.
Yeah.
That's surprising. No, you'll get more questions based on alcohols, phenols, because that in turn will connect with aldehydes, ketones chapter, like rest of the other things also. Ethers has like a few named reactions and all that you have to learn, but it's not like a large portion. It's easy. You guys will be able to cover it. And ethers are one of the more non-reactive compounds, not like alcohols, phenols. So there are limited number of reactions.
Ether वाले में only Friedel crafts and nitrogen one is and electrophilic. Otherwise, there are not many reactions as such.
That's what it's. Ethers are relatively non-reactive compared to all the other compounds, so won't have a lot. Okay. Kaveri, Smira, you guys done with this?
1 second.
Yes, ma'am.
Okay. Sanskriti is still writing or done?
Ma'am, I'm done.
Sanskriti, you're writing completely right. Like these other things matter because give reason question may, isme, like these are the.
Yes, ma'am.
things you need to know.
पूरा लिखा है. Yes, ma'am.
Cool. Hopefully, if we reach production of ethers, then one more class tomorrow will complete the chapter. We'll have time for questions also. Guys, can you study parts about methanol and ethanol on your own? That's more theory heavy. Uses of methanol, uses of ethanol and production.
Yeah, we didn't even do this in school.
Okay. Go through it. If there's any parts that you want me to cover, I'll do it tomorrow. Okay.
1 second.
Let's see.
What have you written before HBr?
3, like 3 places substitution takes place, no? So you get 3 HBr.
Done, ma'am.
Okay. Arya, Sia, yes, done. Okay. Sia? Okay, so that was electrophilic substitution. Others will remain more or less the same. Friedel-Crafts reactions and all. You need to know that it's orthoparadirecting. Special notes about halogenation in this one. So that's what it is. Okay. The next is coal-based reaction. This is important commercially because through this reaction you produce salicylic acid, not acetyl, just salicylic acid, which you use further to produce acetyl salicylic acid and all that. So this not to be confused with coal-based electrolysis. Do you guys remember coal-based electrolysis?
Yeah.
The mechanism was cancelled. I remember that.
That's all I remember. I did that so well, and then I found out that it's cancelled.
Yeah. So this is not electrolysis. This is coal-based reaction. Okay. So you start off with phenol. OH. Treat it with NaOH and you get phenoxide. Normal acid-base reaction. This is something that we've seen earlier also. ONA, salt plus water hoga. So the thing about ONA, the thing about phenoxide ion or sodium phenoxide is more reactive towards electrophilic substitution compared to phenol itself. Okay, so this is more reactive towards electrophilic substitution. So then when you treat it with carbon dioxide and water, H plus ions, carbon dioxide in acidic medium. Now, this happens to be a weak electrophile. Okay, so that is the reason we needed to do this conversion in the first place, make it more receptive towards electrophilic substitution. So then the carbon dioxide with water, so you get, so acidic hydrolysis converts this back to OH and the carbon dioxide gets introduced here as the carboxylate group. So इसका IUPAC name is 2-hydroxy benzoic acid. commonly known as salicylic acid. Yeah, so this is an extremely like commercially important this thing. So yeah, how is it manufactured is through coal-based reaction. Okay, and each step has a purpose. At its core, it's electrophilic substitution. We want to introduce the carboxyl group here, but in order to like, and that is being done directly by using carbon dioxide in acidic medium. But because this is a weak electrophile, we are first converting phenol into sodium phenoxide, make it more receptive, more reactive for electrophilic substitution, and then go ahead with this reaction. Okay, so this is coal-based reaction. So this is salicylic acid used in face wash and everything. Iska esterification karne pe you get acetyl salicylic acid, which is what aspirin is. So pharmacy and all, this is an important.
First, could you explain why it's more reactive towards electrophilic? Point again.
Why? Because this would then exist as phenoxide ion, na? See, phenol ka resonance,
Yeah.
if you get it, यहाँ पे covalent bond hai and oxygen takes on a positive charge. So in the case like, but when it is converted to phenoxide ion, this has more negative charge. It's more stable when the resonance यहाँ पे double bond O होगा and the negative charge gets distributed here. So that be one reaction. Hello. Hello. Yeah. Hello. Can you guys hear me now? Okay. At what point did it get cut off? Like, were you able to?
You were saying why you've written weak electrophile.
Ma'am, I got disconnected. What just happened?
Even I got disconnected.
This also got disconnected.
Oh.
We lost the whiteboard till now, so we'll have to start. So I'm hoping that all of you have completed writing down that reaction, right? Or I'll write it again. Not necessary to write Sia or not written?
I didn't write.
Neither did I.
Shameless.
Okay, so this was the reaction, coal-based reaction. This was the
This
second.
is a type of electrophilic or
It is electrophilic substitution. You're substituting a COH group wahan pe. So you're substituting a COH group from carbon dioxide in acidic medium and H+, but that is an extremely weak electrophile. So with regular phenol, that reaction is very difficult to take place. So what you're doing is converting this into phenoxide ion by treating it with NaOH. This becomes ONA. Again, this is not covalent, so O minus Na plus. And this, when you treat it with carbon dioxide and acid, gives you your salicylic acid, OH and COH. Okay, the carbon dioxide gets inserted over here. So first thing, yeah. So CO2, this happens to be an extremely weak electrolyte. What am I saying? Electrophile. So in order to make the ring stronger, like more receptive to this, we're making this, like we're converting it into phenoxide ion. Now the reason why this is more reactive for substitution than this is the activation. OH may, so like this is more reactive towards electrophilic substitution. So the effect of O minus is more than the effect of OH, because OH may you have covalent bond between O and H. So when this goes into resonance, यहाँ पे positive charge है. So that kind of like positive charge matlab it tries to pull on the electrons towards itself. It's not like wholeheartedly giving it to the ring during resonance. But phenoxide ion excess electrons hai, so this the lone pair here goes in. There is nothing pulling on the electrons from oxygen side. Yahan pe there's a very good concentration of negative charge as the resonance takes place. So that is why we say O minus, like oxide ion, is more activating compared to OH.
So that's why we add NaOH to
Yeah.
make it more reactive.
Yeah. So to convert it into O minus, which makes it more reactive.
I didn't understand. The same thing was happening with OH also, right?
Nay. So the difference is that in the case of OH, yeah, वहाँ पे hydrogen भी है ना, like oxygen is sharing its electrons with hydrogen also.
So there are more electrons involved in delocalization in phenoxide.
No, the same number of electrons are involved, but the effect, when this shares the electrons with it, resonance में, oxygen is getting a positive charge here. यहाँ पे double bond है, H and oxygen. And this goes over here, so minus, and then the other thing. And then, yeah, this continues on throughout the ring, right? यहाँ पे, because there is a positive charge here, that positive charge, it will try to, like, of course, the electrons are going to be delocalized and everything. But you need to remember, like, electrons are in the form of an electron cloud, right? So it's more of electron density, kahan pe sabse zyada hai. So because of this positive charge, there is a slight pull in this direction also. But in the case of phenoxide ion, that pull is not there. So यहाँ पे O minus, same thing.
But wouldn't it also be the case that since now it's not sharing a pair with H, it's like an ion, like it's separate from it's separate now, so won't there be more electrons involved in resonance?
Where is it separate?
But O will still have positive charge now.
Look at
No,
the
like
difference between this and this. So the negative charge that oxygen has is delocalized throughout in the case of phenoxide ion. So यहाँ पे कोई problem नहीं. So like both of them are orthopara directing because of your plus R effect. Plus R effect मतलब क्या? The effect of pushing electrons towards the ring, of including them within the resonance thing. Plus R effect is more in the case of phenoxide ion compared to OH. It activates the ring more. It makes it more reactive. So what part exactly not it, huh?
Miss, if we are making it into phenol, like if we are forming phenoxide ion, which is more reactive towards electrophilic substitution, so then why are we using weak electrophile?
We are using weak electrophile because we want to create this. And because this happens to be a weak electrophile, we are preparing phenol to make it receptive to this.
Huh?
It's the other way around. Our end product is salicylic acid. We want this.
Yeah. So you're using weak electrophile, and for the weak electrophile to work, we are converting phenol into phenoxide.
Yes, that is what is happening.
So इसमें weak electrophile is CO2.
CO2, yes, because we want carboxylate, right? So this is C double bond.
Yeah. So what is that H2 in second step? मतलब it's happening in 2 steps.
My
Or-
mistake. H plus होना चाहिए, H2 नहीं. Hydrogen
Yeah,
gas.
H plus.
Yeah.
So it's happening in 2 steps.
The exact mechanism I have to look into. It's a little more complicated. I can check it. But from my understanding, again, carbon dioxide is a gas, right? So we are we are conducting the reaction in, what do you call it? Acidic medium. We're using acid along with CO2. Let me pull up the mechanism and show it to you.
We're using acidic medium too.
We're using acidic medium along with carbon dioxide, basically.
So
Now this is Riemann-Tiemann reaction. What is reaction? Yeah, I'm just getting, okay, this is the reaction. I'm not finding the mechanism that easily. This reaction mechanism. There you go. Okay. So this is what's happening in the reaction. So phenoxide ion है, in resonance यहाँ पे negative charge आया. So this negative charge attacks carbon from carbon dioxide. This is the start of the CO group getting attached here. So already we have a carboxylate ion, deprotonation हुआ. And so the medium is basically to hydrolyze it. So convert phenoxide in back to phenol and the carboxylate into carboxylic acid. That's essentially it. It's the medium. Okay. Do you guys want to note down the mechanism or press switch?
Ma'am, I still didn't understand the. Can you go back to the whiteboard? I still didn't get the difference between OH and ONega, like the electrons in the locally. Like, won't there be more? I don't understand why there won't be more electrons when it's not. When it was sharing a pair with H earlier, and now it's not. So there'll be more electrons involved in resonance, right?
You see, the number of electrons is the same. Like यहाँ पे double bond आ रहा है, यहाँ पे double bond है. But yeah, you're right. So the electron cloud is more in the case of phenoxide compared to regular phenol.
And then on top of that, the R effect thing.
On top of that, नहीं. Like that is the consequence of plus R effect. दोनों के केस में plus R effect हो रहा है. Just that in this case, it's more compared to this. It's like how we say, like if you talk about inductive effect, compare Cl and Cf. Both of them are pulling on electrons, but F will pull on it more.
Yeah.
So similar thing. यहाँ पे both the cases plus R effect हो रहा है, लेकिन phenoxide में it's happening a lot more compared to in phenol. The effect is more in the case of phenoxide. That's what makes it more reactive.
So the reason is not that because there are more number of electrons, right?
You can, instead of talking about it in terms of number of electrons, phrase it to more electron density. That's what it's doing. It's increasing the electron density here.
In the ring.
Yeah.
Okay, got it.
All right. Sia, Smera, go to the next one.
I'm just 1 second. I'm sorry.
Yeah.
Yes. Should we write that plus R effect wala thing or?
Yeah. So yeah, you can write it as a reason why more reactive, because plus R is more in the case of phenoxide than this thing. Write it completely instead of writing it. The reason is for this is plus R effect is more when O minus is attached than when OH is attached. Okay. So plus R effect more matlab, you can just make a note, increases electron density in the ring. More electron density in this case, slightly lesser. It's still activating the ring, which is why nitration, bromination, all of that's happening at a faster rate. But in this case, it's more than this. We're comparing both of them.
It's plus R effect is more in phenols, na?
Phenoxide, when O minus is attached. This is a general thing, like it's not specific to phenol. In general, if you're comparing resonance effect for oxide versus hydroxy, in this case, it's more than this. Order है ना वो, like inductive effect के लिए resonance effect that way. Okay, Sanskriti done? Okay, Sia, Smera, Kaveri, we go to the next reaction.
Yes, ma'am.
Kaveri?
Yes, ma'am.
Okay. The third one, similar to Kolbe's react in terms of product, very similar to Kolbe's reaction. So this is Riemer-Thiemann reaction. Spelling is always confusing. R-E-I-M-E-R, Thiemann reaction. There's also another named reaction. You will come across this in when we're doing aldehydes, ketones also. Kolbe's में we are introducing COH group, right? इसमें we are introducing a CHO group. So introduced at ortho position. Okay, so on to the reaction. This is again multiple steps. So we have OH. When treated with chloroform, CHCl3 plus the presence of aqueous NaOH, this gives an intermediate called benzyl chloride. So O, Na, यहाँ पे CHCl2. So this is an intermediate called benzyl chloride. So usually when intermediates are enclosed in square brackets like this, it means that they don't stay like that for very long. They're not very stable. They'll immediately change structures. Okay, so solution may NaOH is there. So it'll react with 1 more mole of this, and this gets converted to close to our final product. And this on hydrolysis with H plus, we get our phenol H back. Okay. So this similar to what we had in the previous product. This is called salicylaldehyde. You had an acidic group called salicylic acid. You have an aldehyde group, salicylaldehyde. Okay, Reimer, Timon. I don't know how his name is. Their names are produced, but iska mechanism, we have it readily available. I'm sure that
Is the mechanism?
is there. Like I found lots of versions of it. So once you're done noting it down, if you're curious, you can do that. Else, at this point, this is what you need to know. So, whatever you want.
Why is it benzyl chloride and not benzyl?
Benzyl chloride is this, no? Sorry, this is like chlorobenzene. This is benzyl. Do you remember benzyl, benzoic?
Yeah, so it's benzyl because there's one more chlorine.
Not just that, there's also like oxygen here, lots of things happening. So this is benzyl chloride.
Why don't we say those in the name?
Huh?
Like we use benzyl for all of this. Like why don't we use sodium?
And this is the important part. Like sodium, like if you hydrolyze this, you'll get phenol and CHCl2 anyway. So that's why some cases. So the mechanism I'm seeing, instead of NaOH, they've used KOH over there. So यहाँ पे O minus K plus रहेगा. That's not like the important bit. Like thing we need to know is okay, यहाँ पे phenoxide ion है और CHCl2 is like substituted here.
So in the first step, we would get 2 NaCl as the byproduct, right?
NaCl, HCl, because this is taking place of a hydrogen, right? So either HCl or maybe hydrogen would go off in the medium and you get NaCl. Okay, Smera. So once Kaveri is also done, you guys let me know if you want to see the mechanism or should we go to the next bit. Or I can send the mechanism to you guys on WhatsApp, and whoever wants, you can like just take a look at it.
Just can you show the mechanism?
So you can see, first step may the electrophile is being prepared. So you have chloroform. When it reacts with NOH minus, you have CHCl3 minus. Carbanion is formed, which is stabilized because there's 3 chlorines attached to it. Then this loses a Cl minus. Polarization is happening to create your electrophile. Yahan pe C plus. This is a free radical being formed here. Cl or minus jaake yahan pe free electron hai. Then now phenol, first step reacts with the NaOH or KOH, forms a phenoxide ion. Then during resonance, so this gets into the picture, the radical that's formed here. यहाँ पे minus charge है, तो the free radical is attracted here, then deprotonation happens, the carbon is attached here, all of that happens. So here you have the intermediate benzyl chloride, oxygen here, and then you have C, and you have CHCl2 attached over here. Then this loses a Cl minus. Lots of weird things happening here. The lone pair, like, yeah, this I'm not too clear about what's happening here. But finally chlorine okay. Fir yahan pe there's like oxidation taking place, which is when you're finally getting your double bond O. They produce हो रहा है. And then this is enol. You have double bond and OH tautomerizes to give you aldehyde, salicyl aldehyde.
Is that
What is the
H2O and then
difference?
there's H plus uske niche?
H2O, yes. So like there's H2O being added, there's a H plus being removed, proton being removed. Yeah.
What's the difference between tautomerization and dimerization?
Can
Dimerization,
you tell what tautomerization is? Because I asked Miss and she said she would tell me because it's not in syllabus.
oh, that's weird. So tautomerization is a form of, it's like a specific case of isomerization where there is a rearrangement taking place, and it's like from, so from one functional group you're getting another functional group. Like this particular case, and this is the most common, this is the only one that I have come across in whatever I've studied. So this is called keto-enol tautomerization.
That one is like more stable and one is less stable.
Haven't we done this somewhere? Keto, enol, tautomer.
Oh, like every time there's a product where you have en and all, that always tautomerizes to form a keto group.
I think the other day I had asked you only about tautomerization. You gave this example.
Yeah. So this, like, I have, like, my teachers told me about keto-enol tautomerization, and this is the only case that I have also come across, like, while studying and everything. So I know of keto-enol tautomerization. So it kind of,
wasn't when there was isomerization in 11th one, usme there was functional isomerism also, where is that tautomerism or same ही चीज है?
it depends. Like, it's a very, like, see, resonance may
Because even in that example, there was OH to ketone. Like under a functional isomerism, the example that was given, it was, as far as I remember, it was OH group 2 ketone. So is that tautomerism, or like is functional isomerism and tautomerism the same thing, or?
they're not the same thing. So it is a case of functional isomerism. So suppose I have something like this, CH2 double bond CH, then single bond CH2, यहाँ पे CH2OH. This will not go undergo tautomerization because a double bond or OH are very, very far. But whenever you have a case where they're adjacent to each other, there is going to be rearrangement taking place where these electrons, like basically this double bond comes over here, hydrogen comes over here, and then this tautomerizes into a, यहाँ पे aldehyde here because it's at the end of the chain, but yeah, like it tautomerizes into a.
The example of functional group isomerism was the main one that we studied was alcohols and ethers, right? Like the O car.
Alcohol
Position.
ether is one.
Alcohols to ketone, na? So
No,
only when, so tautomerism is what basically, it's when it's like functional. I don't understand the difference.
Functional isomers are when you have the same molecular formula. So number of carbon atoms, number of hydrogen atoms, number of oxygen, whatever it is, they are the same, but different structures.
Yeah.
Abhi, tautomers are like a specific case of functional isomers. So if you look at this, these two are functional isomers kyunki if you count the number of carbon atoms, hydrogen atoms, oxygen atoms, they will be the exact same. But these two have even more special relationship ki they can, like this species can get converted to the species. So that specific case is tautomerism. Functional isomers
that is
broader thing. Like functional isomers ke liye, you just have a single criteria ki number of, like the molecular formula should be the same, but the structures are different. If the structures are different in a way that they both have different functional groups, it becomes functional isomerism.
But ketoenol tautomerization is a type of tautomerization, right? So how is that tautomerization itself?
Because it is in the conversion between like a keto group and like phenol.
Yeah, so tautomerization by that definition should be functional group to functional group. No?
yeah,
Yeah,
So then that's same as functional
same as
isomerism.
functional group isomerism.
it's not the, like, okay, that's what I said. It is a special case of functional isomerism. Anytime you come across a like a pair of functional isomers, you cannot say that they will undergo tautomerization. It's only under
Okay, so what's an example where it's only functional isomerism but not tautomerism?
like this. Okay, I'll give you guys two compounds.
But इसमें तो functional isomerism भी नहीं होगा क्योंकि उधर सिर्फ OH है. Like
I'll give
you
you
said that the double bond has to be close.
1, 2, 3, 4 na? Haan. Can you compare the molecular formula for both these compounds?
It's the
C4 hydrogen.
the number of carbons, hydrogens are the same, and then oxygen, the position of oxygen is different. So functional group isomer.
Right, number of carbon, number of hydrogens, is it the same? You have 2 plus 1, 3.
Yeah.
2, 5 plus 2, 7 plus 1, 8. Here we have 3 plus 3, 6 plus 2. So both of them have the formula C4H8O.
Yeah.
These two will not interconvert between each other the way it happens over here. So these two will not undergo tautomerization. These two are not tautomers, but they are functional group isomers क्योंकि molecular formula same है, लेकिन structures और functional groups अलग है. यहाँ पे alcohol.
So tautomerization happens when the functional group isomers are able to convert into one another. In this case, it's just that. Okay.
Yeah.
So these two are functional isomers, but they can't switch between the two. So that's why they're not tautomers.
No.
Acha.
So tautomerization is like a special case of this. I'm sure there's like a lot more to it, but at the base, like this is something that you guys will come across every time you have an email. So this is the thing. Okay. All
Miss,
right.
can you please phrase it like functional isomerism, whatever you explained now? Because I'm sure I'll forget.
So I'll do one thing. I'll share the text with you because again, this is not something like I just know of it. I know what it is, but I don't know enough of it to like put it in a proper way.
Okay.
So this is Reimer-Tiemann reaction or Reimer-Tiemann reaction, however it's called. And next, number 4. Reaction with zinc dust. This is a reaction that you guys have studied earlier.
How many of these left?
Last 2. There are small ones, like you don't have mechanisms and all that. It's just reactions that you have to know. So when you heat phenol with zinc dust matlab finely powdered zinc. Basically.
This is the fifth one, right?
5th.
Oh, this is the 4th one.
No, this should be fourth.
Huh.
Third is col base, second is halogenation, and first is nitration.
Oh no, I kept nitration and halogenation under the same because both of them are electrophilic substitution.
Even col base is electrophilic, right?
But it's more than that. It's like a multi-step and it's a named reaction. So, okay. So when you heat it with zinc in the form of zinc dust, you get benzene plus ZNO. So this you must have come across when you were doing preparation of benzene.
Whenever we react with zinc, why do you always say zinc dust? Like, do we not ever react with like the solid zinc metal?
No, you also use zinc granules, no, when you're doing that acid wala reaction.
Which reaction?
10th May, when you were studying about acids, that the fact that acids release hydrogen gas and bubbles are formed. So usme
Yeah,
zinc granules.
the amphoteric wala thing.
That's also there, yes. Amphoteric, yeah, zinc is amphoteric.
It's part of the same thing, like the bubble wala.
ZNO one is amphoteric one. The zinc granule ones was the hydrogen release one, no?
Yes,
They're two different.
end of the day, again, it's all zinc reacting with acids. It's cool. Both of you are right. Zinc happens to be amphoteric. Zinc also happens to release hydrogen gas when it reacts with acids. Same thing.
Zinc oxide is amphoteric, not zinc.
That's an amphoteric oxide. Zinc as a metal also is amphoteric, aluminium and zinc. Okay, oxidation, last one. So phenol on oxidation, again, OH group gets converted to double bond O. So in this case, those compounds are known as quinones. So an example, like, okay, if you are oxidizing phenol in the laboratory, let's say you're using dichromate, acidified dichromate, like Na2Cr2O7, the presence of H2SO4. So this combination is called chromic acid. So in case instead of giving the formula or dichromate, if you're mentioned chromic acid, don't get confused. Like essentially it's the same anion being used here. Okay. So this gets oxidized, strong oxidizing agent. So you get this compound. Oh, sorry. So this is called benzoquinone. So this type of compound is called a conjugated diketone. Okay. Makes sense. Diketone because you have two carbonyl, like two ketonic groups, and they are conjugated. So you have double bond, single bond, double bond, single bond, double single, double single. So conjugated diketone. So this specific compound is called benzoquinone. Okay, so this is in the presence of this sort of an oxidizing agent. In general, like when we were discussing appearance of phenol, we also discussed this. If you leave phenol out in the air, it undergoes atmospheric oxidation. Matlab, it gets oxidized with atmospheric elements also. In that case, you get like a different mixture of compounds. It's not like one specific thing. So it has like different quinones, right? In air, phenol is slowly oxidized to dark colored mixtures containing quinones.
Will we give reasoning on this? Like, why do we store phenol this way?
Yeah, or why does, like, phenol is supposed to be transparent, but this particular bottle in the laboratory was found to be dark colored? Why? Stuff like that. It's again, it's a relatively slower reaction. So if you're not careful, you'll end up with the oxidation. It's not like hydrogen peroxide where you just expose it to light and it happens spontaneously. It's much slower than that.
Also, here we can use K2Cr2O7 instead.
Absolutely.
Also, how does this reaction happen? How do we get double bond O in the bottom?
You want to look at the mechanism? See, again, Cr2O7 dichromate is an oxidizing agent that would be a source of oxygen, just like how permanganate is a source of oxygen.
Oh, say
Yeah, but how the double bond?
So this, again, during the mechanism, see, during resonance itself, some of the CH double bond, like CH double bond, CH breaks, and then they become single bonds, right? Like that's how during resonance it's shifting. So I'd imagine that यहाँ पे double bond है, when this has concentration of electrons, then some reaction shenanigans happen and oxygen is introduced here. जैसे हो सकता है.
Can you show the mechanism?
Let me just pull it up. Phenol oxidation. Again, if I say phenol oxidation, there you go. Found one. Very small. Let's try. Is this visible? Oh, good. It's not losing resolution. Take it. So we have phenol, oxidizing agent. Okay, it loses this thing phenoxide ion. So proper free radical mechanism हो रहा है. So this gets converted into a free radical, then rearrangement is taking place. He told you, like, as this resonates, when it is in this step, conjugated double bond here, then the oxidizing agent comes, attacks it, and then, yeah.
Why that step specifically?
So, like, why?
What is that K and N?
Huh?
What is that N?
N, nitro. Again, okay, I've just Googled images, right? So this is a different oxidizing agent that has been used here. Something with nitrogen. Let's see. Same thing. No, this is reaction. Yeah, that's why you don't come across mechanisms for oxidation reactions that often. It's a little complicated, and there's like free radicals and all involved, so it's difficult. It's the only one I could find. So I'll have to like study up a bit. I'll study it. If I can simplify it, I'll share it with you guys. Because just looking at the mechanism is not enough. It's not that easy. Okay. All right, what else do we have? Yeah, that's it for reactions of phenols. So ethers, we have 10 minutes. So I'll start ethers tomorrow then. Have you solved more questions on alcohols, phenols during this time on Clipper?
No, there was only solutions, na?
Alcohols, phenols bhi assign kiya tha. And I remember previous classes had started doing some questions. At least the preparation methods and all we were on it.
Oh, yeah.
Okay. There's lots. Look, I'm assigning this to you guys. Try and knock it off. Let me see what is your progress of it up. Ethers, skip it. Okay. Arya has reached 50%, Smera 45%, Sia 41, Sanskriti and Kaveri.
I did haloalkanes, but solutions most is numerical based, so I couldn't see the options and stuff properly. So I've been doing all in one, and QB I'm doing now.
Okay. Do it right now because it has been corrected. So at that point of time, there was an issue with
Radio solution thing has been corrected, so I'm getting that. But with the code wala thing, I'm still getting issues. So I'm not able to solve it.
Check it now. Because I like even during live sessions, I used to see that latex was not displayed. Abhi to pura correct hua. The previous session that I took with grade.
Yeah, it's definitely better now, but still there are a lot of interruptions. So I thought it would be better. I'll check one second.
So whenever you come across it, yeah, click a screenshot or
yeah, I tag it.
Send it out. Yeah. No, don't tag. Like if there's an issue with the display, send a screenshot. If there's an issue with the content itself, plus minus
Okay.
galti hui, or like Arya, that time we discussed now, KF value was given wrong. So those kind of cases, then flag the question and the content team will edit it. Okay, so between 40 to 50% you guys are at. Try to knock down at least like 5% every day. So at least in a week, if you guys can get to 70-80%, that'll be good. And then the week after that, you can go up to like 90%. That way, solve it. Yeah. So, Sanskriti, you have to spend a lot more time on this.
Yes, ma'am.
Yeah. Okay, cool. So Kaveri, you were mentioning